today we will discuss the current in strong and weak inversion regimes. So, in the previous lecture we had discussed the linearization of charge and also current with respect to the local channel potential and surface potential. So, we discussed what terms of the current expression are important in strong inversion and weak inversion. So, today we will derive expressions for current in strong inversion regime and in weak inversion regime. Let us first see what is the value of inversion charge in strong inversion regime. We use strong inversion approximation which we discussed in the previous lectures. So, we had Vp is Vg minus Vto by n. So, for a given gate voltage we approximated the value of Vp in this way. This can also be seen, one can recall looking at this figure. So, we are assuming a constant n. So, we would say that minus Vto is n Vp. Okay. Now, what is the value of inversion charge? V minus Vp. So, where V is the local channel potential. So, and V minus Vp in strong inversion is V is larger than Vp. So, V minus Vp is positive. So, there is a negative sign coming here because inversion charge in n channel MOSFET is negative. Now, at the source edge, what is the local channel potential? It is the source voltage. It could be 0, but it is the source voltage Vs. So, at the source edge of the channel near the source, Qi is equal to n Vp minus Vs. Okay. So, now let us try to expand this. So, n Vp is Vg minus Vto. So, you can write this as Vg minus Vto minus n Vs. Okay. So, now let us use this to obtain an expression for strong inversion regime current. Now, let us look at the forward current. So, forward current is you integrate from source voltage to infinite channel potential beta Qi dP. There is a correction, this is actually Qi by Cox. So, what does this become? So, this is, so can we replace now this with Vp minus Vs? So, that is what we do, beta n by 2 Vp minus Vs whole square. How did we obtain this? What is the value of Qi at infinity? When V is tending to infinity, what happens to Qi? Qi tends to 0. Okay. So, when V is tending to infinity, Vp minus V is mathematically it is a negative value, but in reality it will be a 0 value. So, Qi by Cox is equal to 0 for V smaller than Vp. So, that is strong inversion approximation. Therefore, you neglect the value of Vp minus V square when local channel potential V is infinity. So, you write it only for this value. Okay. So, now let us expand upon this using our earlier discussion. So, this would be beta n by 2 Vg minus Vto minus n Vs square by 2n. You can write this as Vg minus Vto square minus 2n Vs into Vg minus Vto plus n square Vs square. Okay, we will use this later. Now, let us look at the current expression itself. Now, let us normalize this current If, I specific is normalized If. So, what is its value? Beta n by 2 Vp minus Vs square divided by beta ut square. Okay. So, now this becomes normalized Vp minus normalized Vs by square by 4. So, normalized Vp minus normalized Vs by 2. So, this is the normalized value of forward. So, let us also look at it from the expression that we had derived in the earlier lecture. So, where we said that Vp minus Vs is 1 plus 4 If. In strong inversion regime, we said that this is the expression that is valid in the previous lecture. So, this since If would be quite large compared to the value of I spec in strong inversion, therefore, this would nearly be equal to 2 root If, and you can see that these two expressions are equivalent. Now, let us derive the expressions for linear regime, the current in linear regime of operation and the current in saturation regime of operation. So, with respect to local channel potential, we have derived where we used strong inversion approximation. So, n is so Vg minus Vto divided by n is equal to Vp. So, using that we obtain that the current is If minus Ir. So, that should be equal to beta by 2n into Vg minus Vto square Vs into Vg minus Vto minus plus Vn square Vs square. So, likewise you get the drain term, because for IR we are integrating from local channel potential being infinite to local channel potential being the drain voltage Vd. So, you would have Vg minus Vto square minus 2n Vd Vgs G minus Vto plus n square Vd square. So, now that turns out to be beta by 2n into Vg minus Vd minus Vs into Vg minus Vto minus n Vd minus Vs. So, simplifying this we get this expression. So, ID is beta into Vg minus Vto minus n by 2 Vd plus Vs into Vd minus Vs. So, this is the expression in linear regime of operation. This is for Vp Vd being smaller than Vp. Okay. What is the value of saturation drain voltage? So, saturation drain voltage is when pinch off happens, and in our strong inversion approximation Vp is Vg minus Vto by n. So, for a given voltage, gate voltage, what is the, so you can identify this is the value of Vp, and in strong inversion approximation we have been assuming that if you plot Qi by Cox minus Qi by Cox with respect to local channel potential, you get a slope of minus 1 and you touch 0 at Vp. So, for a given gate voltage, the value of, when the value of drain voltage is Vp, so that is when the value of local channel potential is Vp, that is where the pinch off happens. So, what does it mean? What is the value of saturation drain voltage? Now, suppose the source voltage is Vs. So, you need to increase the local channel potential till the local channel potential becomes Vp. So, what is the value of drain to source? So, if source voltage is Vs and the drain voltage is increased by Vd, so you have an increase in voltage Vd minus Vs. So, the pinch off to happen at the drain edge, Vd is equal to Vp, pinch off at drain edge of the channel. So, what is the value of Vd sat? So, now that is Vd Vp minus Vs for a given Vs. Vs could be 0. If Vs is 0, Vd sat is Vp. Now, using this, now let us look at simple expression that we derive for saturation current. So, in saturation IR can be neglected, reverse current, because the drain edge of the channel, the channel near the drain is pinched off, and for local channel potential being infinite, again the channel is pinched off. So, you are integrating a 0 charge from the drain edge of the channel to an imaginary point where the local channel potential is infinite. So, therefore, IR is 0. You are in effect integrating from infinite to P the value of Qi by Cox. So, therefore, it is 0. So, what about IF? So, ID is then IF. So, what is its value? Beta n by 2 Vp minus Vs square, that is the value of forward current as we had seen earlier. So, what is this equal to? Beta n by 2 Vg minus Vto minus nVs square. So, this is similar to the expressions that you usually find in textbooks. The only thing is that you have the slope factor which has been taken into account, and qualitatively the expressions are similar. So, now let us look at weak inversion approximation and how the current would behave in weak inversion. Using strong inversion approximation, the value of inversion charge would be 0 at Vp. The value of inversion charge would be 0 at Vp, and using weak inversion approximation, the value of inversion charge would increase exponentially and it would be quite large for small values of local channel potential. But if we use the entire expression that 2 Qi plus natural logarithm of Qi is Vp minus V, then you get this more realistic picture. So, for very small values of V, this would merge with the strong inversion approximation. For large values of V, it would merge, for a given gate voltage, it would merge with the weak inversion approximation. So, when the gate voltage is larger than VTO and Vs is say 0, so in that case near the channel, near the source, the channel is inverted, but since you have a VDS which is positive, so in that case for as you go towards the drain, you keep on reducing the inversion charge, and for Vd greater than Vp, you would find that the channel pinches off for local channel potential equal to Vp. However, suppose you have a different scenario where Vg is smaller than Vto. Now, strong inversion approximation is not valid. So, Vg is now smaller than Vto. What would be the value of Vp? If you use the same slope, if you assume a constant slope factor, then you can see that Vp would be negative. What do you mean by this? That is, so V local channel potential V in weak inversion, local channel potential V is larger than Vp, and we know that local channel potential near the source is 0. Suppose Vs is 0. So, what does this imply? That Vp is negative, or in other words, your gate voltage is so small that the channel pinch off happens already for a 0 source voltage even near the source. So, the local channel potential Vp is negative. So, in weak inversion, see when the device is operating in strong inversion but in saturation. So, near the source the channel is inverted, near the drain the channel is pinched off. So, channel is pinched off wherever the local channel potential becomes V. So, in that case Vp is positive, but the gate voltage is also quite high. Now you are looking at a scenario where the gate voltage is 0 or negative or very small, smaller than VTO. So, in this case, even for local channel potential being 0, you would observe that there is a pinch off, so to say, because in this expression 2 Qi plus natural logarithm of Qi, this would dominate as we had discussed earlier. So, now let us look at the forward current. So, Qi is Vp minus V exponential of Vp minus V, weak inversion approximation. So, what is the value of specific of normalized current, forward current? Qi dB normalized local channel potential, and that is from Vs to infinity. So, what is that? Exponential Vp minus Vs. So, if you look at the absolute value, then it will be If is equal to I specific to exponential Vp minus Vs by U. Now, let us plot minus Qi by Cox versus local channel potential V. We said that it would become 0 at Vp in strong inversion approximation. But if we relax this, then if we again plot local channel potential with VTB, then you would, for local channel potential 0, you would have VTO as the VTB, and still you would continue on the negative side with local channel potential being 0. Now, suppose the gate voltage has a value which is smaller than VTO. What is the value of Vp for this gate voltage? So, for this gate voltage, what is the Vp? Suppose we had another value of gate voltage here. What is the Vp? Likewise, for this gate voltage which is smaller than VTO, you have the value of Vp here. So, what is the value of inversion charge then? So, inversion charge is Vg minus Vp. So, let us expand upon this. Slope n. So, now you are saying that this is the value of Vp for your Vg, and suppose your value of Vs is here, this is the value of source voltage, source potential. Then what is the inversion charge at the source potential? So, from our earlier discussion, it is given by this value. So, what is its value? So, it is again, you can again write it as Vp minus Vs by n. So, this is the expression is similar to what you had in strong inversion. The only thing is Vp is negative, Vs could be a negative or a 0 value, whatever, Vs is larger than Vp. Only thing is here, so that is the only difference, Vs is now larger than Vp. So, using this, we now write an expression for If. So, that is why we get the same expression, similar expression. So, we again use this and get the similar expression, and therefore, our earlier expression for Vp minus Vs also stands, and therefore, If is actually I specific exponential Vg minus VTO minus NVs by n. That is because Vp minus Vs is Vg minus VTO minus NVs by n, that we had derived earlier. And we are saying that similar expressions relating Qi and Vp minus Vs are valid, only thing is Vp is now negative, Vs is larger than Vp. So, what would be the drain current? So, drain current is If minus Ir, and that is I specific exponential Vg minus Vto by n into exponential minus Vs by Ut minus exponential minus Vd by Ut. So, let us rewrite I specific exponential Vg minus Vto by Nut into exponential minus Vs by Ut minus exponential minus Vd by Ut. Suppose Vd is larger than 3 Ut, what would happen to the reverse current? I would be I specific exponential Vg minus Vto by Nut into exponential minus Vs by Ut. So, this is for saturation and this is for linear. Now, it is not neither linear nor saturation. You may want to call it as subthreshold, triode, but it is not exactly. It is not triode, and you may like to call it as subthreshold saturation. So, here therefore, the value of Vd sat is 3 to 5 Ut, the constant. So, in weak inversion approximation, you have an exponential relationship between gate voltage and the current. So, in this lecture, we have discussed the current in saturation in linear regime in strong inversion, and in weak inversion we have derived the current and also how it saturates for the value of drain voltage being larger than say 3 times thermal voltage. Thank you.